Let's just jump right in, shall we? Today, we are taking a massive, zooming out journey from our immediate cosmic neighborhood all the way to the deepest, darkest reaches of the universe. We're going to look at some of the absolute most mind-bending discoveries in space science happening right now, literally from hidden rocks hanging out in our own backyard, all the way out to the colossal engines driving our hunt for dark matter. So, first up, does Earth actually have a second moon? I know, it totally sounds like science fiction. But for a brief window in 2024, the answer was actually yes, we did. Thanks to a really fast-moving object known as PT5, we had a legitimate second satellite for about 2 whole months. And this temporary capture happens because of something called a Hill sphere. Basically, it's a million-mile wide region where Earth's gravity is the absolute boss, completely overpowering the sun's pull. It perfectly explains how passing space rocks like PT5 get snagged in our gravitational net. They become these temporary mini-moons, kind of dipping in for a quick orbital dance before eventually slipping back out into the void. Honestly, because of these crazy gravitational dynamics, Earth really isn't flying solo through the universe. We actually have a whole entourage of quirky co-orbiters. Alongside those transient mini-moons we just talked about, we also have quasi-moons that orbit the sun, but effectively tag along right beside us. Then there are horseshoe orbiters that seem to speed up, swap lanes, and drift back in this massive, bizarre loop. And finally, Trojans. These are rocks parked in cozy gravitational hideouts exactly 60 degrees ahead of or behind Earth. Inner solar system discoveries. Let's push out a bit further. NASA's MAVEN orbiter recently went silent after an incredible 11-year run, right? But its legacy is that it definitively proved exactly how Mars transformed. It finally answered the ultimate planetary mystery: how a once warm, watery, totally life-friendly world became the freezing, barren desert we see today. And the answer? The atmosphere literally vanished into space. See, because Mars lacks a protective, planet-wide magnetic field like we have here on Earth, MAVEN discovered that the solar wind is just constantly blasting the planet. It's literally stripping away about 100 grams of Martian atmosphere every single second. And get this, that rate jumps tenfold during heavy solar storms. Continuing our journey outward past Mars, we hit the Psyche mission. Launched back in late 2023, it's going to use a Mars gravity assist in 2026 to reach its target in 2029, which is asteroid 16 Psyche. Now, this is a heavy, completely bizarre world made entirely of metal. And what's equally amazing is how we're getting there. The probe uses highly efficient solar-electric Hall effect thrusters. Basically, these ion engines use electricity from solar panels to propel the craft, barely sipping a fraction of the fuel used by traditional chemical rockets. Scientists actually suspect this giant metal asteroid is the exposed core of an ancient, destroyed planet. So to find out for sure, the spacecraft is going to execute this highly precise sequence of descending orbits. It's going to progressively zoom in from 700 kilometers all the way down to a super daring 75 kilometers. And every time it drops closer, it unlocks new secrets, from mapping the magnetic fields to firing gamma-ray spectrometers to pinpoint the exact chemical makeup of the metal down below. Exploring Jupiter's icy moons. Let's keep zooming out. Right now, we currently have 2 monumental missions heading to Jupiter, and they're perfectly designed to complement each other. NASA's Europa Clipper is super laser-focused, aiming to execute 45 incredibly daring flybys of Europa. Meanwhile, the European Space Agency's JUICE mission takes a much wider approach. It's studying multiple icy moons, Ganymede, Callisto, and Europa, before eventually settling into orbit around Ganymede. I really want you to consider the massive volume of liquid water hiding beneath Europa's frozen crust. We're talking about a salty ocean containing twice the water of every single ocean on Earth combined. Let that sink in. For astrobiology, this is the absolute ultimate game changer. Why? Because where we find water, energy, and organic compounds, we find the highest potential for life. To actually investigate this, Europa Clipper is packing an unprecedented toolkit. It features the Reason ice-penetrating radar to map subterranean lakes up to 30 kilometers deep, plus a high-gain antenna to measure the moon's gravity field. But honestly, the most staggering piece of engineering on board is SUDA, the Surface Dust Analyzer. Check this out. If Clipper flies through a watery plume out in space and collects a single grain of ice containing less than one bacterial cell, SUDA is sensitive enough to detect that chemical signature of life, just one cell. Chasing interstellar visitors. Let's push toward the edge. There is such an incredible collaborative spirit in space exploration right now. Back in late 2025, the interstellar comet 3I/Atlas, which was a visitor from a completely different star system, passed right through our neighborhood. Because it was totally hidden from Earth's view behind the sun, scientists quickly coordinated this awesome temporary tag team between the JUICE and Europa Clipper probes to analyze its hydrogen, oxygen, and carbon emissions on the fly.
Now, if we follow that comet's path backwards to the very edge of our solar system, we hit the heliopause. This is the absolute physical boundary where the sun's outgoing solar wind is finally stopped cold by the surrounding interstellar medium. It is the exact line where our sun's influence ends and true interstellar space actually begins.
And thanks to the legacy Voyager probes crossing this exact boundary, we have had our minds absolutely blown by what's actually out there. See, we used to think interstellar space was just this empty, quiet nothingness. Not even close. Voyager data revealed a highly dynamic environment. The interstellar magnetic field is way stronger than we calculated, and it's filled with denser, colder plasma that interacts violently with our solar wind to create these massive cosmic shock waves.
Peering into deep space. For our final jump, let's look at the big picture.
Looking out into that deep space, our 3 next-generation mega observatories are operating as this ultimate unified tag team. The Nancy Grace Roman Telescope acts as a wide-lens scout, using its coronagraph to map dark matter and find exoplanets. When it spots a promising target, the James Webb Telescope zooms in with its unprecedented infrared sensitivity. Meanwhile, down on Earth, the Vera C. Rubin Observatory acts almost like a hyper-fast sports photographer, tracking live, transient cosmic changes across the entire southern sky. Just to highlight how extreme the engineering is on these machines, take James Webb, for instance. To keep its delicate infrared sensors cold enough to peer 13.5 billion years into the past, it requires a 5-layer sun shield. This shield provides a sun protection factor, an SPF, equivalent to 1 million. 1 million SPF. And meanwhile, back down on Earth, the Rubin Observatory is completely revolutionizing software engineering. It'll image the sky and process massive, mind-boggling amounts of data to issue automated alerts about cosmic changes, like exploding supernovae or incoming asteroids, in just 60 seconds. That kind of processing speed is just a massive, massive leap forward for astronomy. Knowing what we've just explored, from Earth's secret, co-orbiting moons to oceans hiding beneath Jupiter's ice, all the way out to the dense plasma at the edge of the heliopause, it really shifts your entire perspective, doesn't it? When Roman, Webb, and Rubin fully combine their data, they aren't just taking cool space pictures, they're literally rewriting the laws of physics. So what unimaginable cosmic mystery is waiting to be unlocked next? Keep looking up, and I'll catch you in the next explainer.